Okay, hello everybody. My name is Oliver Hadler. Welcome to this talk on the Cambridge Science Festival. Let me just start share my screen. Right, okay, so my name is Oliver Hadler. I am an institute teaching officer at the Institute of Continuing Education and program manager for the Cambridge Sense Strategic Network at the University of Cambridge, which is connecting researchers and academics in the area of sensing technologies and sensor applications across the university. So my talk today is entitled, "What Can Sensors Do for Us?" As an introduction, maybe I would like to see where you are joining us from, because I'm sort of sitting here in a cool and damp Cambridge. So maybe you're from some more warmer areas around the globe or in the UK. If you could put that in the chat, that might be quite nice as an icebreaker for this session. So while I'm waiting for results to come through, there's always a bit of a delay on this line. I will just continue with the introduction to this talk, and we'll see what comes in through the chat. So this talk will be sort of divided into three sections. I will start with sort of sensors versus senses, to think about what actually a sensor is. Then I will give a brief introduction to the sort of electronics and the history behind the principles of sensors, before I move on to the session on modern sensor applications and the idea of what sensors can actually do for us. So let's start by sensors versus senses. So we perceive our world through so 5 different senses typically, so vision, hearing, smell, taste, and touch. And for that, the human body has more than 100 million natural sensors or receptors in the body, the majority of them in the eyes, but also a lot of touch sensors and about 15,000 hair cells per ear, for example, which you're currently using to listen to my talk. And why do we need these senses? Well, they of course protect us from danger. So, for example, if you see a lion, you might have to make some decisions based on what you see and hear, whether you have to hide or run away. If you look at the rotten food on the top right image, you will be using a variety of sensors like sight, smell, and touch, and you will fuse those sensory information together to form a bigger picture of what is going on, and that's what the sensor technologists would call sensor fusion. Sensors, our own senses don't protect us from everything. For example, we don't have any sensors for man-made or natural radiation because from an evolutionary point of view, that wasn't really necessary. For example, the background radiation from space at ground level is relatively low, so we haven't developed any sensors for that. But of course, maybe if you want to measure radiation from a nuclear power plant, or if you want to measure radiation through X-rays, you need additional man-made sensors to detect this. So some of the sensors we are using are very useful sensors. Here we have a thermometer on the top. We have a smartwatch which can measure time and activity levels. We might have a GPS in our smartphone to determine our location. And there's lots of sensors which we actually really need because, for example, you can't run a factory without sensors. We need to measure temperature, pressure, fluid and gas flows, vibrations of pumps and so on. We have to monitor that in a factory to run it safely and efficiently. And we can't fly modern aeroplanes without sensors. So a typical aeroplane has about 25,000 sensors inbuilt, which generate sort of a hard drive full of data per flight. And those 25,000 sensors really they monitor all states of the aircraft, of the engines, not just the speed and altitude, but really sort of a lot of other parameters which help engineers to maintain the aircraft and also help pilots and airline companies to fly their planes efficiently. So what actually is a sensor? Well, in the broadest definition, a sensor detects events and changes in its environment. And that information is then sent to other electronics. So a sensor is always used with electronics. And that's the key point. That's something to really keep in mind. Because if we look at this picture here again with the temperature sensors, we have the thermometer here on the top, which relies on the thermal expansion of a liquid like alcohol or mercury. But it doesn't contain any electronics. So it's not a sensor, it's not a temperature sensor, but it's a thermometer. The device below fulfills the same functionality. It measures temperature, but it actually has an electronic sensor. So there's a sensor element which reacts to temperature, but generates an electrical signal, which then can be processed, and in this case, displayed on this display here. So this is the difference in a way between a sensor here on the bottom and some other sort of meter on the top. So what are the principles of sensors? I will go a little bit into the sort of physical principles of behind sensors, and then sort of move on to the sort of 21st century applications. As I said, a sensor is always used with electronics. So here's a very simple picture of what electronics is, in case you're not familiar with that topic. We can think of electricity a bit like a water circuit. So on the left, we have a circuit with water, and on the right, we have a circuit with electricity. The water is pumped through this circuit here with a pump, which provides the energy for the water to flow. There might be a valve which can switch on and off the water flow. And as the water flows through this circuit, it might experience, let's say, a very thin tube. And so that kind of increases the resistance for the water to flow through this circuit. On the electrical side, we have the same principles. We have a battery which produces the energy for the electric current to flow. We have a switch which closes the circuit and, for example, switches on the lights or the television or radio. And the resistor is the element which resists the current flow, which converts electricity into useful work. So, for example, this could be a light bulb, this could be, again, could be a television or whatever electrical device, but it will have some resistance to the current. Now, in 1827, so kind of 200 years ago, Ohm sort of came up with Ohm's law, which is a very fundamental law in electricity science. And that relates the current in a circuit with the voltage and the resistance. So we have here the voltage, for example, of a battery. We can measure the current flowing through the circuit, and over here we have the resistance. And the three parameters are related like this. The current equals the voltage divided by the resistance. So relatively straightforward equation. The important bit here is the resistance, because resistance depends on temperature. So if we take a piece of metal, then its resistance will increase linearly with temperature. If we take a semiconductor like silicon, then the resistance will decrease with temperature. And you see the different shape of the curves here. The left ones are linear, they are straight lines, whereas the one here on the right with the semiconductor is curved, so a non-linear relation. How can we use that effect as a sensor? Well, here is a very simple electric temperature sensor based on resistance measurements. So what I have here is I have a circuit very similar to the one I showed before, but now with two resistors. The bottom one here is in contact with an environment whose temperature I want to measure. This circuit here divides the 5 volts from the battery into 2 parts, and I'm measuring the voltage at this point here. The voltage here can be calculated using this equation. And in this equation, we have the values of the 2 resistors, R1 and R2. R2, the resistance of the second resistor, depends on temperature. So as the temperature changes, the resistance of this bottom resistor changes and the voltage here changes. So I have translated a change in temperature to a change in voltage. So I've made an electronic sensor, something which converts a physical parameter into an electric signal. Another effect used in sensing is the photo effect, which converts light into electricity. So if light shines onto a piece of metal, for example, or any other material, in this case it's potassium, then the energy of the light will result in electrons being released from this material. And that release of electrons depends on the wavelength. At shorter wavelengths here in the blue, the energy of the light is very high, and the electrons which come out of the metal get emitted at a high velocity. On the other hand, if the energy of the light is too low, then in the end there's no electrons actually being emitted from this surface. So this is some physics which has been discovered sort of in the 19th century, and we are making use of that nowadays in our camera sensors, which are based on semiconductor materials, which you can see here. So again, light enters or shines onto these image sensors and generates an electron inside, which then flows through the circuit and can be measured as a current. So what we're doing here is we are converting light into electricity. So again, we have a sensor. So now let's move to a real sensor. This is from the early 20th century. It's a radiobarograph from a weather balloon. So this device was attached to a weather balloon which would rise through the atmosphere several tens of kilometers in altitude. And this sort of electromechanical sensor was measuring temperature and pressure. The way this system works is that there is a rotating disk in here, which rotates at a constant speed. And for every revolution, there will be a contact, an electric contact closed, which then sends out a radio signal. In addition to that, you have these bellows here on the left and right, which deform with air pressure, and via sort of a piece of string down here, another contact is moved, which also sits in contact with that rotating disk. And so when the disk is rotating, it's not only sending a signal at a fixed interval, but it will also send a second signal, which depends on the air pressure. And there's also a third device here, which does the same for temperature. And what you can see here on this image on the right is these signals. So here is the F is the fixed signal. So there's one signal being sent here and the next one being sent there. And here you see the signal from the pressure sensor. And you see it appears at this point here, and then at a higher altitude, it appears a bit earlier, a little bit earlier, and so on. So you can see how the distance between the fixed signal and the pressure signal gives you an idea of the air pressure at that altitude. And at the same time, you can measure the temperature here with the other signal. So this is actually an example of an electromechanical remote sensor. So it goes up in the atmosphere, it measures temperature and pressure, and it sends that data via a radio signal to a ground station. Now, if we move forward for about 75 years, we end up with a smartphone. So here we have the main board of an iPhone 4. In the middle, we have the microprocessor of the phone itself. But I'm not really interested in that one. I'm actually interested in this device here, which is an accelerometer. Now, this looks relatively boring from the outside. It's a sort of 5 by 5 millimeter box, a black box. But the interesting thing is really what's going on inside. So inside we have sort of a micro machined device, and you can see here the length scale here is 20 micrometers. That's sort of a fifth of the diameter of a hair. So you can imagine sort of a hair would be sort of this size. And we have here we have a mass and a spring. So when this device moves, this mass will react with this spring. And over here, there are capacitor plates which change their displacement as this sensor moves. And I'll show you a cartoon video of this on the next slide. This device is called a micro electromechanical system, or MEMS. So this is essentially sort of the modern equivalent of the sensor I've showed you on the previous slide. So here is a little cartoon of this, how this device works.
The sensor consists of a signal processing chip and a micromechanical comb-like structure. These combs form a capacitor, and the distance between the microstructures determines its capacity. The blue part of this structure is movable. Depending on acceleration or deceleration, they change their position relative to each other. The resulting change in capacitance is detected by the integrated electronics, converted into a measured value, and output into a voltage signal.
So you could imagine having these kind of sensors nowadays also in weather balloons to measure similar things as the one I showed earlier. And of course, these devices are sort of the key to the motion sensors we have in smartwatches. So another type of sensor I mentioned already, I mentioned the physics about it, is the image sensor. And here on the left, you have a typical image sensor for a camera. And on the right-hand side, there is a sort of microscope image of how these sensors actually look like inside. So you see the red, green, and blue sort of sub-pixels. So always sort of a set of 4 pixels here, 2 green, 1 blue, 1 red, form 1 pixel, but taking a color image. And to give you an idea how about the size, so this is the size of a human hair compared to the pixel size here. So again, we are working with very tiny structures in modern sensors. And that's really sort of the development that happened. So we had the physics of sensors from the sort of 19th century, and then we have this massive miniaturization in the 20th century to end up with sensors we can use today. Now, I was just wondering if I should take some questions before I move on to the next part of the talk, which would be then of modern sensor applications. So if you have any questions, put them in the chat, and I will have to wait a little bit because there's a bit of a delay on the system here. But I hope you got this idea of some of the physics behind the sensors and how that is sort of translated into real devices. And in the next part now, I will talk about how we are using these devices in modern applications without going too much into the details how each of these sensors work, but the idea is always the same. They convert some sort of physical property into an electric signal, which then can be further processed. So I got one question through now, which is, will sensors continue to shrink in size? Probably yes. The question is, when do we run into problems in terms of manufacturing? So I showed you the micromechanical devices. They're at the size of micrometers. There are moves towards making them even sort of nano size. So we can still shrink these devices further. We can also think about using nanomaterials as sensors. So yes, we can still shrink these devices further down. I think there are no other questions coming through here at the moment, so I will just continue in the interest of time. So in terms of modern sensor applications, I've picked 3 broad areas. healthcare, the environment and agriculture, and smart and sustainable living. A lot of societies experience an aging population, and that brings with it an increase in chronic diseases and healthcare costs, and simultaneously a potential decrease in quality of life for old people. But sensors can sort of help us in this scenario, where we can think of smart, continuous healthcare systems. So the person here on the left is wearing a number of sensors, for example, motion sensors or heart rate, respiration rate sensors. The data gets sent wirelessly to the cloud, to the internet, and on to people like working in the emergency services, your friends and family, or clinicians, who then can use that information from these sensors and plan the correct intervention. And this will be something I will be coming back to again and again with all the applications I'm showing you. The idea here of having some sensors attached to somebody or something, the data will be sent to sort of a central data repository or a data center where information can be collected and decisions can be made. So it's a two-way flow of sort of information and intervention. So here's one example of a wearable healthcare sensor. This one continuously measures vital signs like heart rate and activity and body temperature. So we have the, for example, the temperature sensor here. We have the activity sensor with the accelerometer. This sensor can be worn on the patient. And you can see this woman here is walking around without wires in a hospital environment. She can be continuously monitored. So she doesn't rely on a nurse coming around several times a day to take measurements. So the clinicians can continuously monitor her state of health. And so this should lead to a much better patient outcome at the end. Another example is the wearable glucose monitor. As you can see one here on the right, so they're the size of a finger or fingertip. The way they work is they are electrochemical sensors. So here in the blood capillaries, you have the glucose, which then travels from the bloodstream into the interstitial fluid, so fluid which sits between the cells, and eventually gets to the skin. And then at the skin here we have this electrochemical sensor which uses an enzyme to react with the glucose. And as part of that reaction, electrons are produced, which can be measured as a current. A very small current, just a few nanoamperes, but you can detect this current there. So here we are converting the concentration of glucose or any other chemical into an electric signal. So again, we have a sensor. The output is an electrical signal. The benefit of this sensor is that you don't need, if you're diabetic, you don't have to prick your fingers and take the test like that. But here you can actually continuously monitor glucose levels of round the clock. So it's really partly of a life-saving device, but it's also much more convenient than doing finger pricks several times a day. Another electrochemical sensor could be this one here, which is used for cancer detection using volatile organic compounds in the breath. So what you are detecting here is chemicals like methanol, acetone, and sort of other hydrocarbon compounds in your breath. Again, you have an electrochemical sensor. There's sort of there are electrochemical reactions taking place which convert the concentration of these volatile organic compounds into an electric signal. If you take those signals and that data, you can then try and infer whether a person has cancer or some other illnesses. So it's sort of a non-invasive way of detecting illnesses. So moving on now from the healthcare applications to the sort of environmental and agricultural arena. One big area of sensors are weather observations, which are important, for example, to monitor climate change, but also for disaster mitigation or providing information to traffic, the utility companies, or agriculture as well. So what you can see here is really a range of sensors which measure temperature, air pressure, wind speed, humidity, lots of physical parameters. These sensors might be here on a surface station, your typical weather station you might even have at home. You have sensors on ships or on aircraft. These remote sensors here, they send their data to satellites, which then send the data back to sort of a central data processing station in the national Met offices, essentially. They collect all the data and run the computer models to provide you with weather forecasts. So what you really need here is a lot of sensors. So we have about 11,000 land-based sensors across the world, and about 4,000 ships and just over 1,000 buoys sort of floating in the oceans, taking thousands of temperature and pressure measurements around the clock. So the more data you have and the more accurate it is, or the better the geographical spacing, the better your weather forecast. And if you're a little bit older, you probably realize weather forecasts are getting better with time, because we have better sensors and we have better computer models. So without the sensors, our weather forecasts wouldn't work. Another area of sensors here is remote environmental monitoring. Here is an example to monitor forests. So what you can do is you can take essentially a camera and put it onto a satellite or onto a drone, but you're not taking any sort of normal camera. You're taking a camera which can split the image into lots of different colors or wavelengths. So this might be 10 different wavelengths or colors, or up to 100 different colors. And so you actually, for each position here, you get a stack of images, all taken at different colors. Those colors, so you can see here the color as wavelengths, and you can get the reflectance here. So that's the amount of light reflected from the surface. And you see that soil and water and vegetation reflect light differently. So by using an image sensor, what I've showed you before, with 3 different colors, here you're using an image sensor with 100 different colors, you can detect what's on the ground just by using these images. And here on the right is an image of a forest. So using this hyperspectral imaging together with height measurements through LiDAR, which is kind of a form of radar, you can actually find different trees or different tree species in a forest, which of course is very useful if you want to monitor how a forest develops over time. Here's another sensor in the sort of environmental monitoring space. This is a mobile air pollution monitor. This was developed by a team of students in Cambridge a couple of years ago. This sensor sits or can be put on the back of a bicycle, and you measure, or this sensor here measures particulates, so tiny particles in the air, which get into your lungs and cause health problems. And you can see here sort of a map, somebody cycling through Cambridge, and you see sort of traffic hotspots or air pollution hotspots in the city. Now, in terms of making these sensors maybe smaller and smaller, this is a possibility for, in future, integrating these kind of sensors into a smartphone, for example. So you might be walking around with a smartphone which has one of these sensors miniaturized built in, so you know what the air pollution levels are where you're walking. I mentioned farming already for sensor applications, and here is sort of a cartoon of how a smart farm might look like. So the farmer now actually relies on sensors for decision making and getting the best out of the farm. So here, for example, we have a weather station, or that could also be remote weather data from the global network of weather information. The farm might have some soil moisture sensors, and all these sensors feed together into sort of a central hub, which can help with the decision making. And very often this kind of data will be presented on a smartphone to be sort of in a user-friendly way. So one of the difficulties here is you can collect all the data, but you have to make sense of the data. So it's the idea here is the flow of sensor data and transfer that into actionable information. That's sort of the key in these systems. So here's an example of a remote moisture sensor. It's a relatively simple device. It just relies on the fact that water conducts electricity, or in a way the resistance of the soil changes with temperature, with moisture. So this is again kind of a resistance measurement, but not depending on temperature, but depending on moisture. Here's another example of a sensor for agriculture. This is a sensor which you can use during the transportation of products. So this one here, for example, measures temperature and acceleration, again with the MEMS accelerometer. They're sort of built into this device here, which looks a bit like a fruit. So you can put that artificial fruit within your real fruits, and you can measure the environment during transportation. So if somewhere during your road transport or so you experience a lot of vibrations, you can go back to the road haulier and check what they have done to your products. Or for example, if the cooling in the refrigerated lorry fails, you can detect that with the temperature sensors. Smart agriculture also relies on image sensors. So here we have a drone with a camera. You can monitor the color of the leaves, so you can see how well your crops are growing. But you can also detect potential diseases like this one here. So you have an opportunity here as a farmer to detect these kind of diseases early before they spread. So you can imagine you have a big farm, you fly this drone over this farm. You don't have to physically walk through it, but you just have this drone flying almost continuously, taking images, and maybe with a machine learning algorithm or artificial intelligence, it can pick out these diseases very early on. So our future of farming might really be looking like this, where we have these sensors here planted in the field. They don't look terribly exciting. They're sort of in ruggedized plastic boxes, but what's inside it, that's really that's where the sort of technology comes in. As a user, you will have a smart device here, a smart display to communicate with the sensors. And the sensors, together with, let's say, automated watering systems and temperature controllers and so on, they will allow indoor farming to be very well controlled and hopefully increasing the yield of products with less fertilizer and less energy consumption. So let me move on to one other aspect of sensor use, and that is smart infrastructure, so railways and roads. We have a lot of infrastructure in use, but it's very difficult to add further infrastructure to it. So if you want to widen a road, if you want to build a new railway line, that is very difficult because of environmental and space constraints. But what you can do is you can digitally enhance your infrastructure. So you can make better use of the existing infrastructure. So that would be, for example, having better signaling systems on railways to have trains running at shorter intervals or closer together. So you can transport more people on the same rail line. And we can use sensors here to monitor our infrastructure. So here, for example, is a strain sensor attached to a bridge, and it sends its data wirelessly to a central node. So what you get here is a lot of data from the sensor in terms of strain and vibrations. And again, here, the trick is to interpret this data. So we get a lot of signals here, but what do these signals actually mean? So this is, again, it's an example of converting data into information. There's a big drive to use machine learning and artificial intelligence in this area, because you don't want to sit there as a human trying to analyze all this data. So a computer can do that faster and better. But this is kind of where we are going nowadays with sensors. Which leads me to this concept of digital twin. So here we have a piece of infrastructure, a water pump in a water purification site or so. And we are constructing a virtual digital twin of this device. So there's a lot of sensors on the physical device, measuring, for example, rotation speeds or noise and vibrations and temperatures and so on. And we can use that data and sort of simulate a virtual copy of the physical object, and then use these sort of simulations to maybe predict or detect potential problems. So we can take action before the actual problem occurs. So that's a very sort of interesting concept being sort of introduced, for example, here in sort of civil infrastructure, but also in healthcare or in aerospace. So overall, our vision of what sensors can do for us is this vision of a smart and connected future. And you've seen already some examples where I always mention sensors and wireless connections. So here we have a range of these scenarios where, for example, here the smart home, where every device is connected to the internet, and ultimately these devices are sensors. Or we have a smart city where you have sensors distributed around the city. The data is collected at a central point and then disseminated to the users. Or you take the smart car, the driverless car, which uses a lot of sensors to be able to navigate traffic. That's a whole different topic. You can spend a whole lecture on that. So I'm not going into this. But you can see the idea of having lots of sensors being connected in a network and then somehow displayed either on a, for example, on a phone or on a smartwatch. I mentioned the smart city. That's not something in the future. It already is happening. So we have the smart cities, the intelligent cities, where you really sort of connect all these sensors together to provide useful information to the citizens. So here's an example outside the Cambridge railway station. There's a big display here with, for example, bus information or travel information. The data which feeds this display comes from the buses themselves. So if that system knows where the bus is, it knows when the bus will arrive. So you actually have up-to-date travel information. So that really sort of brings me to the end of this talk. And really what I can say here at the end is what sensors can do for us is really up to our or your creativity. So you take whatever sensors there are, you connect them up, you collect data, and then it's up to you what you are doing together with what you're doing with that data, how you convert that into useful information. So thank you very much. Let me know if you have any other questions. I can answer one of the earlier questions, which is how is a thermal infrared sensor different from others? The infrared sensor is a contactless sensor. You don't have to bring it in physical contact with the object you want to measure the temperature of. It measures the amount of infrared radiation, which depends on temperature. So in a way, it's not quite a hyperspectral sensor, but it's a sensor which uses a different part of, it's an image sensor which uses a different part of the electromagnetic spectrum. I'm just waiting for some questions to appear in the chat. Or If you're typing anything in the chat, it hasn't come through yet. Okay, so there's one question. What is the state of the art for sensors being able to detect when they are broken or becoming degraded? That's a good question. And the answer to that is you probably need, you would monitor what's coming out of you would monitor the data coming out of the sensor. And you can't necessarily distinguish whether the sensor is degrading or whether the piece of equipment it is attached to is degrading. So you will have to have a look at the physical object and at the sensor and decide whether it's the sensor which is not reading the correct data, or whether it's, and therefore degrading, or whether it's the physical object having some problems. And you can probably, if you would be really concerned about the sensor being correct, then you would have several sensors measuring the same parameter. And or ideally, for example, you have 3 sensors measuring the same parameter. If one of them gives you different data, then that sensor is probably failing, but you can't be 100% sure. Okay, I'm still waiting for more questions to come through. Don't be shy, you can ask anything related to sensing. Okay. Are there any particular concerns in your mind about systems of sensors being hacked and or privacy issues? Yes, that's so privacy and data security is a big issue in sensing. you can imagine if you have, I mean, there are stories about hacking into smart devices at home, smart doorbells and things like that. This is maybe a relatively small problem in a way, because it affects your doorbell, it affects your house, which of course is a problem for yourself. But if you then think about sensors being distributed around the whole city, if you hack into that system and manipulate data in that sensor system, or you bring those sensors down somehow, you're running into potentially big problems. You would potentially shut down a whole city. You could potentially hack into healthcare sensors, which again can have drastic consequences. So there is real concern about the use of sensors and privacy and security. We will see what happens over the coming years. I think it's, in a way, it's very similar, I would say, to the internet. We are all happy to use the internet, but we also know there are constant threats in terms of viruses or networks going down. Okay, so it looks like there are no more questions. So thank you very much for attending this talk, and I hope you've learned something about sensors and what they can do for us. And as I say, it's up to your creativity. So if you're interested in sensors and what you can do with them, there's a lot of information on the internet. You can use Arduino microcontrollers. They're easy to program. You can attach all sorts of sensors to them. You can use a Raspberry Pi. There's a lot of stuff to play with as a hobbyist. And if you are working with sensors in some way in your professional life, of course, you know there's a lot of potential. So, well, thank you very much, everybody.